Welcome back. In this video, you will learn how to find the area of surfaces of revolution. Let's get to it. Alright, so previously we have seen how to calculate the volume of solids of revolution via the disk, washer, and shell methods, but now we are interested in calculating the surface area of similar figures that we call surfaces of revolution. And so a surface of revolution is formed by revolving a curve around an axis of revolution. And so if you take a look at this graph right here, we have a function y equals f of x, and a particular portion of that function, a curve with length L from A to B, and if we were to take that curve from A to B and revolve that around the x-axis, we would form a surface of revolution. Right, it would not be a solid of revolution because we're not revolving the region beneath that curve around the x-axis, we are just revolving that curve. And so it's just going to form the outside of what could be a solid of revolution, but it's just a surface of revolution. And so if we were to do that, if we were to revolve this curve from A to B around the x-axis, it would form a surface of revolution that has circular cross-sections. And we could continue to draw these circles for the entire length of the curve from A to B, and you would start to see the surface of revolution form. Right, I could connect these circles down here, and now you can see the surface of revolution. And this is different from our solids of revolution because there is no volume inside this figure. This is more of a shell, if you will, of what could be a solid of revolution. Right, but this is just a surface or the outside of that solid. And so if we wanted to calculate the surface area of a surface of revolution like this one right here, note that the surface would be made up of circles from A to B, just like we have drawn here. And so if we know what the measurement is around the outside of a circle and multiply that by the length of that curve, that will give us the entire area of that surface. And so the measurement around the outside of a circle is known as the circumference of the circle. And the circumference of a circle is equal to 2 pi r, where r is the radius of the circle. And the radius of our circles is the distance from the axis of revolution, which is the x-axis in this case, to the curve, or the function y equals f of x. And so this measurement is the radius in terms of x. Right, so the circumference of those circles would be equal to 2 pi times the radius in terms of x. And so 2 pi times the radius in terms of x will represent the circumference of a particular circle of our surface of revolution at a particular value of x. And so if we were to multiply that circumference by the length of the curve, that will give us the area of the entire surface. So the surface area will be equal to 2 pi times the radius in terms of x times the length of the curve. But now what is the length of the curve? Well, in our previous lesson where we learned arc length, we learned that the length of a curve could be found by using a definite integral. And that definite integral looks like this. The arc length is equal to the definite integral from a to b of the square root of 1 plus f prime of x, or the derivative of our function, squared times dx. And so we could combine this definite integral, which represents the arc length, with the circumference of one of the circles that would make up that surface. And so we would have that the area of the surface is equal to the integral from a to b of 2 pi times the radius in terms of x times the square root of 1 plus f prime of x squared times dx. And so what this definite integral does is it calculates the area of this surface by adding up the circumference of an infinite number of circles from A to B, where each of those circles has a thin width that is determined by the arc length of the curve. Right, so when we calculated the arc length, we were adding up an infinite number of small line segments that make up the length of that curve, and so those really small line segments will make up the width of our really thin circles from A to B that together form a surface of revolution that we can calculate the area of. Okay, and so this is our definite integral that we will use to calculate the area of a surface of revolution that is formed by revolving a line around the x-axis. But what if we were to revolve this curve around the y-axis instead? Well, if we denote that, let me erase this arrow around the x-axis, and then I'll draw it around the y-axis here. if we were to revolve this curve around that axis, we would form a different surface of revolution, but note that the arc length of the curve is not going to change. The only thing that's going to change here is the radius. The radius is no longer the distance from the x-axis to our curve, it is now the distance from the y-axis to our curve, right? Our new axis of revolution to that curve. And so if I make a note of that this distance right here is the radius, we could still represent that radius in terms of x. We don't actually need to work in terms of y to calculate the area of this surface of revolution. Because what would the radius in terms of x be? Well, the radius of our circles, if I were to draw one circle as a demonstration here, the radius of that circle is the distance from the axis of revolution to the curve, which just happens to be a value of x. Right, wherever we choose to draw a circle along this curve, the distance from that point on the curve to the axis of revolution is just whatever value of x you are at along the x-axis. And so in this case, r of x is just equal to x. Okay, and so since the arc length of our curve doesn't change, and we can still express our radius in terms of x when we're revolving around the y-axis, the only difference in calculating the area of a surface of revolution formed by revolving around the y-axis instead of the x-axis is that our radius is just going to be equal to x. It will no longer be equal to our function where the curve comes from, right? It's not going to be f of x anymore. Instead, the radius in terms of x will just be x. And so in summary, here are the two formulas that you need to know for calculating the area of surfaces of revolution when you want to work in terms of x. When you're revolving around the x-axis, the area of the surface is equal to 2 pi times the integral from a to b of the radius in terms of x, which is determined by your curve, times the square root of 1 plus f prime of x squared times dx. If you're revolving around the y-axis, it's the exact same formula except the radius is now just x. Okay, and so this is what is nice about calculating the area of surfaces of revolution compared to calculating the volume of solids of revolution, is that we don't have to change the variable we are working with, such as switching from x to y, when revolving around a different axis of revolution. However, if you are given a function in terms of y, you could still work in terms of y if you wanted to, but those formulas will look a little bit different. And I'm going to show them to you here, but just know that they're not going to be used very often. You're pretty much always going to want to work in terms of x when you're calculating the area of surfaces of revolution. But if you have to work in terms of y, here are the formulas you would need to know. Right, so if your curve comes from a function x equals g of y, then you could use these formulas. So if you're revolving around the y-axis and your curve is expressed in terms of y, then the area of the surface is equal to 2 pi times the integral from c to d, which are two values of y, of the radius in terms of y times the square root of 1 plus g prime of y, the derivative of g of y squared, times dy. And if you're revolving around the x-axis, then the radius in terms of y just becomes y. Okay, but once again, you're probably not going to use these formulas. You are most likely only going to be working in terms of x, but if you for some reason need to work in terms of y, these are the formulas that you would use. All right, and so with that, let's take a look at an example problem where we calculate the area of a surface of revolution. All right, so here's our first example. We want to find the area of the surface formed by revolving the graph of f of x equals x cubed on the interval from 0 to 1 about the x-axis. All right, and so let's start by drawing our curve. Let's graph the function f of x equals x cubed and take a look at the curve that's going to form our surface of revolution. And so I'll draw the y-axis here, and then I'll draw the x-axis, and then I'll label them. So this is the y-axis, and that's the x-axis. And now let's graph f of x equals x cubed. We know that the x cubed function looks something like that, and so I'll label this as f of x equals x cubed. And then we know that the specific part of this curve that we are revolving about the x-axis is from x equals 0 to x equals 1. And so this would be x equals 0, and then I'll say that x equals 1 is right about here, which means the point on the curve at x equals 1 will be about here. And so this curve right here is the curve that we were going to be revolving around the x-axis to form a surface of revolution. And so I'll just label that with an arrow. so that we remember what axis we are revolving around. Okay, and so if we revolve this curve around the x-axis, our surface would look something like this. You can see these circles that would be formed. And so we have this surface that looks a bit like the outside of a cone. And so if we want to calculate the area of that surface, we will use the following formula, that the area of the surface is equal to 2 pi times the integral from a to b of the radius in terms of x times the square root of 1 plus f prime of x squared times dx. All right, and so let's start setting up this definite integral by using everything that we know about our surface of revolution. And so we know that our bounds of integration are the two values of x that our curve lies between, right? So our curve starts at x equals 0 and stops at x equals 1. So far we can have that this is equal to 2 pi times the integral from 0 to 1. And now what is the radius in terms of x? Well, the radius will be the distance from our axis of revolution, the x-axis, to our curve. And so this distance right here is r of x. And in this case, that distance is just going to be equal to the function where this curve comes from, f of x equals x cubed. And so r of x is equal to x cubed. All right, so then back to our definite integral, we'll have x cubed times the square root of 1 plus the derivative of f of x squared. And f of x, of course, is the function where our curve is taken from. So we have f of x equals x cubed. And so if we take the derivative of x cubed, f prime of x will be equal to 3x squared, right? That's just using the power rule for derivatives. We multiply the exponent down and then subtract 1 from the exponent, so we have 3 times x squared. And so f prime of x is 3x squared, which means that f prime of x squared will be 3x squared times dx. All right, and so with that, we have now completely set up our definite integral that represents the area of the surface of revolution formed by this curve revolved around the x-axis. And so if I clean up my work here, we can begin to solve this definite integral. And so I'll simplify. This will be equal to 2 pi times the integral from 0 to 1 of x cubed times the square root of 1 plus 3x squared. And so if we square 3 in x squared, that will give us 9 times x to the 4th power, and then don't forget dx. Right, so 3 squared is 9, and x squared is x to the 4th power. And so now what we have here is a definite integral that we should be able to solve using an integration technique that we are familiar with. For this specific integral, we are going to want to use u-substitution because we have a composite function within our integrand, right? We have the square root of 1 plus 9 times x to the 4th power. That is our composite function, where the outside function is the square root, and the inside function is 1 plus 9x to the 4th power. And so we're probably going to want to set the inside function of the composite function equal to u, but we want to make sure that the derivative of that function can be found within our integral as well. And remember that the derivative of x to the 4th power will be x to the 3rd power. Because of the power rule, we will subtract 1 from the exponent. And so thankfully we have x to the 3rd power being multiplied to the composite function. And so u-substitution is going to work here if we set u equal to 1 plus 9x to the 4th power. And so if we do that, if I set u equal to 1 plus 9x to the 4th power, and then we take the derivative of that with respect to x, we'll have that du dx is equal to the derivative of 1, which will just be 0, because the derivative of a constant like 1 is just 0. And then the derivative of 9x to the 4th power will be 4 multiplied down and then subtract 1 from that exponent of 4. So we have 9 times 4 times x to the 3rd power, and 9 times 4 is equal to 36, and so the derivative is 36 times x cubed. Now if we multiply both sides by dx to solve for du, we'll have that du is equal to 36 times x cubed times dx. Now whatever du is equal to, that needs to be found within our integral so that we can replace it with du when we rewrite this integral in terms of u. Now I see x cubed dx in our integral. X cubed is here and dx is right here, but I don't see 36 but that's not a problem. We can divide both sides by 36, and so if I do that, we'll have that du divided by 36 is equal to x cubed times dx. And so now we can replace x cubed and dx in this integral with du divided by 36. Okay, and so if we rewrite this integral in terms of u, we'll replace x cubed dx with du divided by 36 and 1 plus 9x to the fourth power with u. And so we'll have that this is equal to 2 pi times the integral from 0 to 1 of the square root of u times du divided by 36. Okay, and so if I clean up my work here, we can simplify this integral by pulling 1 divided by 36 to the outside, and so we'll have that this is equal to 2 pi divided by 36 times the integral from 0 to 1 of the square root of u times du. And now we have a pretty simple integral in terms of u that we can integrate. And so remember that you can rewrite the square root of u to be u to the 1/2 power, and that will help us see more easily how we're going to use the power rule of integration. And so we'll have that this is equal to pi divided by 18, right? Because 2 and 36 can both be reduced by a factor of 2, and that will then be multiplied by u to the power of 3/2 divided by 3/2. And that is evaluated from 0 to 1. Right, so the power rule of integration says to add 1 to the exponent, so 1/2 plus 1 is 3/2, and then we divide by that new exponent. All right, but then remember that dividing by a fraction is the same as multiplying by the reciprocal of that fraction, and so instead of dividing by 3/2, we can multiply by 2/3, and so this will be equal to pi divided by 18 times 2/3 times u to the 3/2 power, evaluated from 0 to 1. Now if I clean up my work again, we can pull this 2/3 outside and multiply it by pi divided by 18, and then replace u with what we set it equal to so that we can evaluate it at 1 and then subtract the evaluation at 0. Right, because these bounds of integration right here are in terms of x, and so we can't plug them into u. We first need to rewrite u in terms of x. You could also plug your bounds into what you set u equal to and get bounds of u if you wanted to, but I'm not going to do that in this case. I'm just going to substitute back for u. And so what we'll have here is that this is equal to 2 pi divided by 18 times 3, which is 54, times 1 plus 9x to the fourth power to the 3/2 power, evaluated from 0 to 1. All right, so we pulled this 2/3 out, multiplied it by pi divided by 18, and then we replaced u with what we set it equal to, 1 plus 9x to the fourth power. Okay, and so now we can evaluate this expression at 1 and then subtract the evaluation at 0. And so this will be equal to 2 pi divided by 54. We can reduce that by a factor of 2 in the numerator and the denominator, and we'll have pi divided by 27, and then that will be multiplied by 1 plus 9 times 1 to the fourth power to the 3/2 power minus 1 plus 9 times 0 to the fourth power to the 3/2 power. And that will be equal to pi divided by 27 times 1 plus 9 times 1 to the fourth power. 1 to the fourth power is 1, so 9 times 1 is 9, plus 1 is 10, so we have 10 to the 3/2 power, minus 1 plus 9 times 0 to the fourth power. 0 to the fourth power is 0, times 9 is still 0, plus 1 will be 1. So we have 1 to the 3/2 power. Okay, and so if I clean up my work one more time, this will be equal to pi divided by 27 times 10 to the 3/2 power minus 1, right? 1 to the power of anything is just 1. And so this is our final answer. We're not going to be able to simplify this anymore, but that's not a really satisfying answer. And so if you plug this into your calculator to get an approximate value, you'll find that the area of the surface is approximately equal to 3.563 and some more decimals. And so either one of these answers is acceptable, as they both represent the area of the surface of revolution formed by revolving this curve around the x-axis. All right, let's look at another example. So here's our second example. We want to find the area of the surface formed by revolving the graph of f of x equals x squared for the values of x between 0 and the square root of 2 about the y-axis. All right, and so let's start by just graphing our function. Let's take a look at that curve that we will be revolving around the y-axis. And so here is the y-axis, and here is the x-axis, and I'll label them. So this is the y, and this is the x. And then let's graph f of x equals x squared. That is the function we are working with in this case. And we know that x squared is a parabola that points upwards, and the vertex is at the origin. And so that will look something like this. That will be the function f of x equals x squared. And we're specifically looking at the portion of this function from x equals 0 to x equals the square root of 2. And so this point right here would be x equals 0. And then we can say that x equals the square root of 2 would be right about here. And so that would be this point on our curve. And so this curve right here is the curve that we are going to be revolving around the y-axis to form a surface of revolution. And so I'll draw an arrow around the y-axis there. And now we can draw a brief sketch of what our surface of revolution will look like. If we revolve this curve around the y-axis, we'll have a surface that looks a little bit like a bowl, right? So that's what it would look like. And so the area of that surface can be calculated using the following formula. That the area of the surface is equal to 2 pi times the integral from a to b of the radius in terms of x times the square root of 1 plus f prime of x squared times dx. Okay? But now in this case, since we're revolving around the y-axis, the radius in terms of x is just going to be x, right? The distance between the axis of revolution and our curve is just whatever value of x we are at along that curve. And so this distance right here, the radius, r of x, is just equal to x, right? So r of x is equal to x. Okay, and so let's set up everything that we have so far. We'll have that the area is equal to 2 pi times the integral from a to b, where a and b are the values of x that our curve lies between, right? So our curve starts at x equals 0 and ends at x equals the square root of 2, and so our bounds of integration will be from 0 to the square root of 2. And then our radius, in terms of x, is just x as we determined. So we'll have x times the square root of 1 plus f prime of x squared. And so now we need to find the derivative of the function that our curve came from. And so f of x is equal to x squared. And so if we take the derivative of that, we have f of x is equal to x squared. Then f prime of x will be equal to the derivative of x squared. Now we'll use the power rule for derivatives here by multiplying the exponent down and then subtracting 1 from that exponent. So we will have 2x, right? We multiply down 2, subtract 1 from 2, and you have a power of 1. So the derivative is 2x. And so if we go back to our integral, we will have 2x squared and then multiply by dx. Okay? And so now we have an integral that represents the area of the surface of revolution formed by revolving this curve around the y-axis. And so all we have to do to find that area is solve this definite integral. And so let's simplify it a little bit. This will be equal to 2 pi times the integral from 0 to the square root of 2 of x times the square root of 1 plus 2x squared. And 2x squared will be 4x squared, and then we still have dx. Okay, and so just like with our previous example, we have another integral that is going to require u-substitution because we have a composite function in our integrand. And so the square root of 1 plus 4x squared is our composite function. And so if we set the inside of the composite function, 1 plus 4x squared equal to u, we need to make sure that the derivative of that function is also within our integral. Now in this case, the derivative of x squared is going to be x to the power of 1 because of the power rule, right? Our exponent will decrease by 1. And on the outside of the square root, we have this x to the first power. And so I think this is going to work out. U-substitution should work just fine. And so if I clean up my work a little bit, let's set u equal to 1 plus 4x squared. And then let's take the derivative of that with respect to x. So we'll have du dx is equal to the derivative of 1, which is just 0, since the derivative of all constants is 0. And then the derivative of 4x squared, we'll multiply the exponent down and then subtract 1 from that exponent. So we'll have 2 times 4, which is 8 times x to the power of 1. All right, and so 8x is the derivative. And now if we solve for du by multiplying both sides by dx, we will have that du is equal to 8x dx. And now whatever du is equal to, that needs to be found within our integral. And so I see an x and a dx. X is right here and dx is here, but I don't see 8. So I'm going to divide both sides by 8, and that will give us a term of du that is equal to something in terms of x that we can find within our integral. And so we'll have that du divided by 8 is equal to x times dx. And now we can replace x times dx with du divided by 8, and then replace 1 plus 4x squared with u, and our integral will be rewritten in terms of u. And so we'll have that the area of the surface is equal to 2 pi times the integral from 0 to the square root of 2 of the square root of u times du divided by 8. And so now our integral is written in terms of u, and so now we can simplify and integrate. And so if I pull this 1/8 to the outside, we'll have that this is equal to 2 pi divided by 8 times the integral from 0 to the square root of 2 of the square root of u times du. And we can rewrite the square root of u to be u to the 1/2 power, and that will help us see how to use the power rule of integration to solve this integral. And so this will be equal to pi divided by 4, because 2 pi and 8 can be reduced by a factor of 2, and that will be multiplied by u to the 3/2 power divided by 3/2, evaluated from 0 to the square root of 2. Right, so the power rule of integration says that we add 1 to our exponent and then divide by that new exponent, and so 1/2 plus 1 is 3/2, so we have u to the 3/2 power divided by 3/2, which is that new exponent. All right, and so then remember that dividing by a fraction is the same as multiplying by the reciprocal of that fraction. So instead of dividing by 3/2, we can multiply by 2/3, and so this will be equal to pi divided by 4 times 2/3 times u to the 3/2 power, evaluated from 0 to the square root of 2. And so now if I clean up my work, we can pull this 2/3 to the outside and then replace u with what we set it equal to. That way we can evaluate it at each of our bounds, which remember, these bounds are values of x, and so we cannot plug them into u. We need to rewrite u in terms of x first. Okay, and so this will be equal to pi divided by 4 times 2/3 times 1 plus 4x squared to the 3/2 power, evaluated from 0 to the square root of 2. Right, so I pulled this 2/3 out, and we replaced u with 1 plus 4x squared, because that's what we set it equal to. And so we have 1 plus 4x squared to the 3/2 power, and it's still going to be evaluated from 0 to the square root of 2. All right, and so let's simplify these two fractions. And so this will be equal to 2 pi divided by 12, but that can be reduced to pi divided by 6. So I'll just rewrite that. We will have pi divided by 6 times this expression evaluated at the square root of 2. So we'll have 1 plus 4 times the square root of 2 squared to the 3/2 power minus the evaluation at 0, which will be 1 plus 4 times 0 squared to the 3/2 power. All right, and so if we simplify, that will be equal to pi divided by 6 times 1 plus 4 times 2, because the square root of 2 squared will be 2, and 4 times 2 is 8, and then 8 plus 1 is 9. So we really just have 9 to the 3/2 power minus 1 plus 4 times 0 squared, and 0 squared is 0 times 4 is still 0, so plus 1 will be 1, and so we have 1 to the 3/2 power. So I'll write 1 to the 3/2 power. And remember that 1 to the power of anything is just equal to 1, so I'll rewrite that, and we'll have 1. All right, and so if I clean up my work again, we can actually simplify 9 to the 3/2 power, because that would be the same as taking the square root of 9 and then cubing it, right? We could rewrite this to be equal to pi divided by 6 times 9 to the 1/2 power cubed. If you multiply these exponents, you still have 3/2. So this is the same expression, and then we're still subtracting 1. And 9 to the 1/2 power, or the square root of 9, is equal to 3. And so this is equal to pi divided by 6 times 3 cubed minus 1. And 3 cubed is 27. So this is equal to pi divided by 6 times 27 minus 1. And 27 minus 1 is 26. And so this is equal to 26 pi divided by 6, which can be reduced by a factor of 2 in the numerator and the denominator, and we'll have our final answer that this is equal to 13 pi divided by 3. And so that is the area of the surface of revolution formed by revolving this curve around the y-axis. All right, and so with that, that is all I had for this lesson. If you want to see some more examples, feel free to check out my examples video that I'll have linked at the end of this video, as well as in the description below. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now, so I will see you next time.